All right, let's get started. So we're coming back on to virtualization. Okay, today is all day, all virtualization. So we had talked about these basic blocks, about the fact that what happens is there's this translation from basic blocks, which is starting at some address and continuing until the sooner of what? Right, what's the end of a basic block? A jump or any sort of control flow change. So return, a jump, a call, or 12 instructions just because we want to have a little bit. And those instructions get converted. So here we have a basic block starting at 1, 2, 3, 4 of here. And then we have another basic block that continues on here. And foo itself is a basic block like this. Okay? So this is almost nonsensical instructions I just made up, doing some moves from registers to registers. Okay? However, what happens, so let's say we boot the machine here, or somehow we just start executing at 1, 2, 3, 4. It's going to go ahead and modify this, right? And call foo is really call, I don't know what this is, 2, 5, 7, 8, let's say. Right? So it's going to convert that. Can it just turn this into call 2, 5, 7, 8? I mean, can this instruction stay as it is? This move instruction? Yeah, that one's fair. We'll leave that alone. Okay? But this call routine has to change because we can't just jump to 2, 5, 7, 8. In fact, let's even back up a second. We're going to convert this. So we convert this to a block. And the block is going to be move %EAX to %ECX. And then we're going to have something we're going to do with the call, right? Okay, which will turn basically into a, back up a second before I look at this contents. And then where is this in memory? Is it at 1, 2, 3, 4? Can't be at 1, 2, 3, 4, right? Because that's where our old instructions are. So this is going to be at some new, let's call it 5, 7, 2, 4. That's what this is, okay? And we're going to also keep a map that says 1, 2, 3, 4 goes to 5, 7, 2, 4. So if anyone ever tries to ask what is the code that we should run at the original address 1, 2, 3, 4, it's over here.
Wait, sorry.
True.
I'm not confused. So just stepping back a second, the whole point of binary translation is to find offending instructions. So in many instances, many of these instructions will remain the same.
Like a move, for example. Yes.
Okay.
But if we did find, what would be a good example? Give me an example of something that's privileged.
Set the CR3 register?
Okay, yeah, so yeah, some CR3 register. We want to do something with that. Then we're going to go ahead and modify that. Okay, in fact, let's look at what we're going to do if we do a set instruct, so turn interrupts off. Okay, which we can't do from CPL3, but we can do from CPL0, right? So if we want to turn interrupts off, we need to change that. So we've got, what is it? What's the instruction to turn interrupts off? Yeah, CLI clear instruction. So we're going to convert that into something completely different. All right? And what we'll do is actually convert that into some code into, remember we have this list of VM information, right? And one of the things in there will be the state of the interrupt flag. So we're going to convert this to somehow, just sort of an assignment. All right? we're going to be storing this in space, right? So this is going to be stored in space that the guest OS doesn't have access to. So if we look over here, right, here's the guest OS, and here's our VMM. And we're going to protect this via segmentation. So every segment is going to limit to only going to this, except for the special G segment. So the G segment can get into here. All other segments are limited to the guest OS. Okay? So therefore, that means that the vCPU flags are in here. If we want to read what the state of the interrupts are, it'll turn whatever instruction that is into a read from this location. We have this GS register that lets us get into here. So we can have code in here that we execute, and we can also have data in here, neither of which is accessible to the guest OS. Except what if the guest OS uses the GS register? Right? They just have some code in their binary that uses the GS register. Can they get access into here? No, because we're doing the translation. We can look and we say, oh, you're using the GS register. We're going to modify that. We'll make the code use the D register instead, or the D segment, sorry. The G, yeah, segment. So we'll make it use another segment instead, and there'll be a little more code perhaps to make that happen than was originally there, but we'll make it so it all looks the same, right? And one of the things about the G segment is it's not used that often. So this works pretty well. All right, so the question is, okay, so this is going to be call into a continuation, which is here. And this continuation is going to basically say, translate at 1, 2, 3, 4, and then let's just leave it at that for the moment. Okay, I don't know exactly how this code happens once it's done, but let's just look at this for a moment. So translate it 1, 2, 3, 4. So we do this, we do this. So we have created this, and now we start executing it. So we start executing, we do this instruction, we do this instruction, and this is going to now go into here, and it's going to say, okay, translate whatever's in 1, 2, 3, 4. So it's going to now take this basic block, which hasn't been translated yet, so it's unsafe. It'll translate it. This will go over here, translated. We'll add to our map. We are calling foo. 2578. There's foo. This is getting translated because this guy's already translated, right? This guy's translated over to here. So now we'll mark down that 2578 is whatever this is. 9996. What's on the what I actually want to look at is the return in here. Okay, once we get to the return. Well, let's say, so once we do the translate of 2578, we now know 2578 is at 9996, and we can go back and change this to to be just a jump to 9976. So we do the translate one time, and then we can just indirectly go to where we want to go. Okay. When we're getting to the return, the question is what's on top of the stack. Okay. What we want to be on the top of the stack is what would have been on the top of the stack when we originally executed, which is going to be 1238, the next instruction to execute. So we'll have 1238 on top of the stack. So what that means is when we do a return, that's going to actually get translated into some code that pops the address from the top of the stack and then jumps to it. Can we jump to this? No, what do we have to do? Look in the hash table and see if it exists. Does it exist? It doesn't yet. 1238 isn't there yet, because that's a basic block we have never executed. So since we have never executed, what do we have to do? Translate it. Okay? Put it in the hash table, and then go from there. Does that make sense? Go ahead.
So when you update that, so after the first time you translate, you actually translate the instruction. You just update that block right there?
Actually, this one here,
Yeah.
I am not sure whether it actually updates this or it goes back to where it was called from and updates there.
But it definitely doesn't update that, the very original thing.
No, this stuff is read-only. We don't mess with that.
So
True.
just at a high level, is the basic cycle here, you have a block, translate, execute, block, translate, execute?
Sort of. We start with block, translate, execute. Yes. That execution can then hit another translate, which will cause us to translate and then execute. Or that execute may just cause us to execute other stuff. So once we have done the translation once, this code, when we're running, is going to go to here, is going to go to here, is going to go to our translated code for here, and we're not actually going to jump into translate. So I guess here's what it is. Read a basic block, translate it, execute. As we start executing, we may be doing one or more translated basic blocks, just until we get to something we haven't yet translated. And then it'll translate that one, and then go on and so on. And keep in mind the translated code has code in it that will look stuff up in this hash table. So when we do a return, the return is going to turn into look stuff up in the hash table. And if it finds it, execute it. If not, translate.
This is the premise of a just-in-time compiler.
Yeah, this is exactly a just-in-time compiler. Yes. And part of the reason it's just-in-time, there's several. One is it's slow to translate the whole thing. But the second is you don't know what the whole thing is. That's the key thing. You just don't know necessarily even what parts of your binary are executable code as opposed to data. And I'm going to claim you can't know in the general case. But you can know where you start, and you could know what the instructions are until you get to a control flow change.
How does it know when entries in the hash table are invalid, or does it just have to wait till the end of the executing program?
What would be invalid? What do you mean?
Or not invalid, but it feels like this takes up a lot of memory to do the translations and then keep all the translations around.
What you can do then is if you do this intermediate step like I talked about here, then you can view this as a cache. And if you want to get rid of something from the cache, you can remove it from the hash table and just change this to be a translate again. So, but it does take some memory, yeah, for sure. And I'm trying to remember, for the paper talked about some version of Windows, I don't remember the XP or something, and how many basic blocks it had. And I remember it was on the order of around 800,000 or something, which seems surprisingly small actually to me. But, okay. All right, so this is the hardware way to do it all. It's kind of a lot of work. And so then the hardware virtualization, right? And this paper was just after the first implementations of hardware virtualization existed in the Intel and AMD. And the basic idea, here's what they could have done. What they could have done was say, okay, in order for x86 to be virtualizable, we've got to fix these problems where the state of the current protection level leaks. And we've got to make sure that anything that operates differently in CPL 0 versus CPL 3 will trap when it's in CPL 3. If they did that, it would have been virtualizable. Instead, what they said is, and part of this is, there's all this code out there that relies on the behavior of the instructions in CPL 3 mode, right? They like leaking, right? They're looking at it, and it will break if they suddenly stop leaking. So, the idea is, just have the hardware keep a duplicated state. So, we have all of the registers. And this includes things like the CPL level, includes the page CR3, okay? And we're going to just duplicate them. And we're going to keep 2 copies, all right? One for the VMM and one for the guest OS. And so since this guy has a CPL level, what CPL levels can the VMM be in? 0 or 1 or 2 or 3, right? Since this has its own CPL, it can be in 0 or 1 or 2 or 3. All right? So that's how we're going to run our guest OS. It is going to be able to switch CPL levels because it just has its own CPL levels. But some of what we want is this guest OS not to be able to take over the machine. So for example, what do we want to have happen on interrupt? So we get an interrupt to come in. Where should that go? Let's say it's a timer interrupt.
From the guest OS?
From the actual hardware, because we actually have a hardware timer. So the hardware timer goes off, yes.
It should go to the VMM first.
What if it doesn't go to the VMM? What if it goes to here?
Then the guest host can just keep all of the CPU time for it.
Guest host can keep all the CPU time, right? The guest OS can keep all the CPU time and not let this guy give time to anyone else. So therefore, timer interrupt needs to go here. What about a page fault? Actually, I'm not going to get into page faults because we have to talk about the page tables, and we'll talk about those in a moment. So, well, in fact, let's talk about them now. It has its own CR3, right? So it has a page table. Mapping what to what? Guest's virtual address to guest physical address, right? And this guy has a mapping that maps to from, as far as these guys are concerned, guest physical, I don't know why I'm saying T, address to host physical address, a real physical address, right?
That's the shadow table.
That's, no. So the shadow table is a one-step thing that takes us from here to here. So what the virtualization said is, let's just provide 2 page tables, and let's have the hardware be smart enough to use 2 page tables. So when you use an address here, you're running, and so there is the idea of which mode you're in. This mode is called root mode, And this mode is called
Yes.
non-root mode. Or guest, but yeah. Root and non-root. Yes?
Why do we have guest stuff on the left? Shouldn't that page table be host virtual addresses, host physical addresses?
A guest physical address is a host virtual address. Right? Those are the one and the same thing. I was a little unsure what I wanted to write down here, but that's the same thing as a host virtual address. Okay? Because this may be filled with addresses not just for this guest OS. It might be for another guest OS, or it might be for just some other process. So more accurately, it is a host virtual address. But if we're thinking about these addresses, that is a guest physical address.
I mean, there doesn't have to be a one-to-one mapping between guest physical addresses and host virtual addresses, though, right?
All of
Yes.
the addresses must have
Let me give you an example. So let's say you have it is exactly the same as environments, right? So let's say we looked at an environment and thought of an environment as an environment physical address. Because as far as an environment is concerned, it can think of those as physical addresses. Environment physical addresses map to JOS virtual addresses, right? Okay. We might not have a mapping for a particular physical address. There might be a page here that has no mapping here. That's certainly possible. Just like in an environment, in JOS, we have this whole address range, but some of it might be empty. Here, we might have this whole address range of things that go in here, but it might be empty. There might be no physical address that goes to it because the VMM might do all sorts of fancy stuff.
So, should we think of root and non-root mode as like parallel to 0 and 3? Like, could you?
Orthogonal from 0 and 3.
Okay, so like if you were in root mode, you wouldn't necessarily be able to do everything that you could do in 0, even though its relation to non-root.
If I'm in root mode, I could very, very well not be able, I'm still limited if I'm in CPL3 as to what I can do. And there's still leakage, and there's some stuff that'll cause me to go to CPL0.
Wait, so do all interrupts first go to the root?
Oh, so we're back all to that. So back to page table, which is why we got here. So let's say we get a page table interrupt. Or we get a page table fault. Where should it go? And let's first look at the normal case where we don't have a page fault. So we use a virtual address. It goes to the physical address, and then it goes to the next page table and says from that physical address to a real physical address. And if there's no faults, that's what happens, and it just works. Okay, your question.
So you're working in non-root mode in the guest OS, and you get a page fault.
We're not even getting page fault yet. We just access the memory,
Yeah.
and it goes from here to here, goes from here to here, and finally finds a physical address.
Page fault would be in root mode then, because it won't know that it faults until it gets down to the page table in root mode, right? Yeah.
Depends. Where did the fault happen? You can fault here.
Okay.
If you fault here, where should the page fault go? This guy. What if you page fault in here? This guy. Does that make sense? Okay. So you could specify something like this. Or, since it sometimes needs to go here, you could also just say it always goes to the VMM, and the VMM has to redispatch it to here. And certainly that may be the case in some things, where basically on each interrupt you can specify where does it go. Okay. So if you've got a device that's you've got some particular PCI device, or a piece of hardware that you want this guy to control, you can make sure the interrupts go to here. But even if you couldn't cause the hardware to do that, the VMM could just keep track. Oh, once I get an interrupt here, send it on to here. It would just be an optimization to have the hardware directly send interrupts where we want.
So the thing that makes me uncomfortable about the guest physical address being the same as
Yeah.
the virtual address is, let's say that the let's say that our operating system in the VMM like wants to have something mapped at virtual address 0, say, and then let's say that the OS we're emulating wants to allocate a physical, what it thinks is a physical page at physical address 0. Then according to this model, it seems like we have to, like there has to be a one-to-one mapping between this guest physical address that's at 0 and our host virtual address at 0. So it seems like we're giving the, you know, the guest operating system some control over a virtual address space, so it doesn't.
Yeah, so another way I think I could pose your question would be if we have two guest OSs, which have the same address range.
That is also a problem.
Yeah, that's a good one. So that is interesting. This is not an exact page table. And now I see kind of how I got this wrong, and I apologize for this. So where's my picture of our stuff? So we have guest OS info, and it'll include all the registers, and it includes, I believe, an EPT for, I think about it, I believe it's an EPT for each guest OS, where an EPT is an extended page table. So we're not actually just using the CR3 from here to the CR3 from here. I apologize for that. So since it is unique to this guest OS, then we can have guest virtual addresses as what we're mapping from. Okay? Don't let it worry you too much. There are two levels of page tables, and the hardware knows how to go through both of them. Okay? But yeah, you're obviously right. Okay. We need to be able to get from here to here and back. There needs to be ways to go back and forth. And so we have some new instructions. Give me an example of some of our new instructions. VM run. So the first time you're creating a non-root mode from root mode, you can start it with VM run. The second and subsequent times you use, I don't know if it's up there. No, that actually goes back the other way. So we have VM enter. Okay? So VM enter, do that. There's a VM exit. Which can be explicit, but is more often implicit. Like, you got a timer interrupt, and you're running in here. That's going to cause you to VM exit back into root mode. Very similar to how an interrupt is going to take you from CPL3 to CPL0. Okay? And in fact, if you get an interrupt, it would take you out of non-root mode into root mode. And then, since it's interrupt, we'll take you from CPL3 to CPL0 in here. And then there's also a VM call. So think of this kind of like a system call up to the VMM. Now you may say, how could this ever want to make a system call up? Well, maybe it is actually knowledgeable that it's running in a virtual machine and wants to talk to its master, right? It's sort of like just talking to God, you know, and saying, oh, environment, if I were running in a simulation, please do this for me. Okay. Yes?
What if you had multiple guests and they simultaneously would do like a VM call or VM exit? Then like...
So when you say simultaneously, are they running on a single CPU? Then how many of them are running at I mean, only one is executing at a time, right?
Oh, I see. Okay, so then 2 CPUs.
They got their own idea. If we got 2 CPUs, they got their own idea of root mode, non-root mode, all the values, all these registers, everything else, right?
So there's never like a problem with like accessing the VMM at the same time?
No. Okay. So, At the time, the VMware paper never talks about these two-level hardware support because it didn't exist, I believe, at that time. So, is it fully true? Yes. So, what happens is, right, we have these, again, two page tables. The guest page table, the extended page table. The hardware just takes us right through that. And that's great. Is it fully great? Which is faster? A shadow page table like we talked about, or this two sets of page tables that we provided in hardware virtualization? Which runs faster? Shadow, because?
All the way from guest virtual all the way to host.
Yeah, you have fewer things to look up. So that's faster. But what are the downsides? How about maintenance, which is easier to maintain? Yeah, the EPT and the guest page table, right? The guest modifies the guest page table. The VMM modifies the EPT. And you don't have to worry about trying to figure out when the guest is making changes and do this stuff. Okay? So overall, which is better? Sometimes right, so we've got the nice thing about the software virtualization is you've got lots of flexibility, okay? So that we can turn, for instance, turn on interrupts or turn off interrupts into just simple assignments that go change values. Whereas if you have turn on interrupts, turn off interrupts in hardware virtualization, if you're in let's say you're in CPL3 here, and you turn on and off interrupts. What happens exactly? That one's a bad example, okay? Because it's going to turn on and off these fake interrupts, and that's relatively quick too. So there are some cases where the software virtualization can eliminate having to go back to the VMM, okay, that the hardware doesn't. Precise exceptions, so figuring exactly when an exception occurred, like between what two instructions, can be harder with the software virtualization because we modified the code and now we have to go report it back at the original instructions. Okay. System calls, we don't have to have the VMM be involved with. If we do have a system call over on this side, when we're in CR3 mode, the system call just does the normal thing of causing the interrupt and going into CPL0 mode here and doing just what it normally does. So a little bit of the, oh, and this just shows some of the timing in booting or halting XP. And this was back when, with the first version of hardware virtualization provided. And we can see there are some cases where the hardware was a lot slower. It was the experience of VMware and papers like this that encouraged, and VMware has done a lot of papers along the way, that encouraged really better hardware virtualization. So the next thing we're going to talk about is new stuff that was provided in terms of hardware virtualization. Okay. And truthfully, VMware's approach is no longer popular. The basic reason is it's a lot of software you have to write. Even if you can make it in some cases faster, it's a lot of software you have to write, and it's much easier to write something using the hardware virtualization. Okay? And we're going to talk about something like Iommu and so on. How do shadow structures stay updated with primary structures? So how do you keep a shadow page table updated with its guest OS page table? And basically, you just need to catch. There are
What does BT stand for again?
binary translation. So here's one thing you could do to keep a shadow page table populated. So here's my shadow page table. And I'll just make it basically empty for the guest OS virtual address space. And so that means any guest virtual addresses that are used are going to cause a page fault, right? So what do I do on a page fault? I go look at the guest OS page table and I see what they got there. And then I fill it in. So I see what they have there for their guest physical address. And then I go figure out what the host physical address should be. And then I put an entry in there. And as long as they stay in that page, we're running fine. If they try and go outside that page, we get another page fault. So we can fill it in on demand. Alternatively, we could write protect the guest page table, and that way be notified when changes are made to it and update this page table on the fly. It's not on the fly, as these changes happen to the page table. Does that make sense? All right. How are instructions that cause an exception forwarded to the... I didn't write this down right. How are instructions that cause an exception forwarded to the VMM handled? So when an exception occurs, again in this binary translation case, who handles it? Does the guest OS handle an exception? The VMM handles it. And then it determines whether to pass it on to the guest OS or not. Okay? The information about registers in a virtual CPU is stored in memory. Right, this is the, well, so let's take that back. So the information about the register in a virtual CPU, where exactly is it stored? So if we're doing this binary translation, where is EAX stored? EAX. Where is, basically all the registers are stored in the registers, except like CR3 is not, right? Because we can't write CR3. So therefore, that's stored in memory. Where else is stored in memory? The GS segment, right? That one is overwritten and used by the VMM. So therefore, there's a copy of it kept in memory of what the value should be. Does that explain that question? Binary translation, does it work for more complex virtualization, a language like Java and a JVM? One thing about Java and a JVM is you know where the code is, which is a big advantage. Okay? So and yes, this is used a lot. Hotspot technology, it's sometimes called. So that's part of what makes Java as fast as it is, because of the fact that we've got this binary translation that goes on. And it gets instrumented and see how many times this is executed. And if we execute it once, maybe we won't translate it, but if it's executed more than once, we will translate it. And we will submit it to optimization, depending, again, on how much time is spent in it. One thing, by the way, about this cache of basic blocks, translated basic blocks, if you think about starting up your OS, there's a lot of initialization that happens, and you never revisit those basic blocks. So that stuff can be fall out of the cache nicely.
If you don't need to do, like if you know, so I guess like why we did binary translation is because of the like difficulty of telling the difference between code and data, right? And so in Java we don't have that difficulty, so why not just compile it all at one, like compile it beforehand and then just running it?
You've got the startup cost. So one known problem of Java code is when you start it, there's a latency. And so you really want that startup to be fast. If, for example, you are spinning up a Java process to handle an incoming web request, you can really badly affect your latency by having to start it up. So you don't want slow startup, okay?
And compile, and not doing just-in-time compilation with results to slow startup, because you have to compile everything.
If you compiled everything when you first started the program, yes. Okay, you could think about doing it once and then saving it on disk or something, but then there is also this, the fact that we have different levels of optimization depending on how often, you know, what's the hot code, what's the code that's being executed most of the time. No? Okay. RISC and CISC. Anyone familiar with RISC and CISC? It'd be interesting. So x86 is CISC or RISC architecture? CISC. So CISC is complex instruction set. And what's the C? RISC, complex instruction set. Computer. Yeah, and this is a reduced instruction set computer. So here's what happened. Instruction sets got more and more complicated, okay, during the 60s and 70s and into the 80s. So that is x86, that's the all the IBM 360 and so on, yes.
Is ARM an ARM processor?
So yeah, let's do this one. x86, ARM. Okay, what? So we got these complicated instructions, complicated enough that actually, anyone heard of microcode? So microcode is basically, we have the raw CPU, and we have our instruction set. And the way these instructions work is not via gates and circuits and so on. Instead, there's code that runs here called microcode. So if you have a return instruction, there's actually microcode for that instruction that says, okay, pop from the stack, you know, go to there, just breaks up these instructions into simpler instructions. Well, there was the microcode, so some computers actually had programmable microcode, so you could actually change the instructions or introduce your own or change, you know, user-provided ones. But what happened is the number of cycles for instructions got to be long, because every instruction here takes one or more microcode instructions. Okay, so you might take 1 cycle, 2 cycles, 10 cycles, 20 cycles to execute an instruction. So we had a speed problem there. And there were crazy instructions. So some architectures would say, we're going to provide a very nice call instruction, for example, which will do the following. It'll set up a frame pointer, and it'll do this, and it'll do that, and it does it all, like, you know, in hardware, at least via microcode. So compiler writers will love using this. And the compiler writers almost uniformly don't like to use that, because maybe it does something they don't quite need, right? And so they just resort to doing a few instructions to do what they want. That turns out to be probably quicker. So if you look at sort of an 80-20 of the most popular instructions, let's see, is that how I want to look at them? Yes. And then we look at kind of either area or time. Let's look at area on the die. They're not using 80% of the area on the die for the processor. They're using maybe this amount. And the other 20% are taking up the rest of it. And similarly for time as well. So the RISC folks said, this is professors at Stanford and UC Berkeley, said, what if we just got rid of all that complexity, made simple instructions. Every instruction is going to take 1 cycle. Okay? And if you need to do complicated things, you need to have multiple instructions. So these complicated instructions would have things like search through this array of memory for a certain string. Wouldn't it be neat if you had an instruction that would do that? Well, yeah, in a weird case, maybe, but yeah. So. Let's see. So how is this similar or different? Push work to software. RISC basically is push work to software, but make stuff fast. So make the instructions we provide very fast. These are sort of the primitives that are provided, and then let people do what they want to do with that. And with the extra space on the die, what do? What do you use it for? Cache. Right? So all of a sudden your access to memory is much, much faster than the other guy. So
What do you mean by die?
by die, what I mean is the surface, the actual silicon for the hardware.
Okay. And by hardware, you mean CPU?
I mean the CPU. Yeah. So when you go, buy your x86 CPU, it's in a little package, and if you unpeeled the package, you look, and there's the little piece of silicon. And so it's that silicon of a certain area, costs money, right, to have that. And what do we want to use that area for? We can use it for circuitry, or we could use it for cache. So it's kind of the same idea here in the hardware versus software virtualization. One thing you could do is move stuff into hardware. The other thing you could do is take stuff out of hardware. Or have just very simple primitives in hardware, which is kind of what some of the VMware folks have argued for. Their approach is interesting because they can switch off between using hardware and software. So they can do binary instruction, but they could also maybe take advantage of the root mode, non-root mode. And no difference in security. As long as you don't have bugs in the VMM, and you don't have bugs in the CPU, they're the same.
So then, are is the RISC architecture kind of more of an abstracted version of the CISC architecture? Kind of like with the CISC architecture, you kind of have more power and granularity of things you're allowed to control and stuff, kind of, or?
The CISC architecture, I would say, is more abstract than a RISC architecture.
Oh.
So the RISC architecture says just take it to its bare essentials. For instance, I'll give you a good example.
Yeah.
If you want to move something from 1, 2, 3, 4 to, I'm going to think I can do this on, there are many machines where you can do this. So you can say, I want to move something from one piece of memory to another piece of memory. RISC says, forget that. You got to move stuff to registers, and then work it in the registers, and then you can move it back. So you're not allowed to have both of these be addresses. Or RISC would say, I'm not going to have an instruction like 12 of, percent EAX, move that into EBX. If you want to do that, add 12 to EAX and then indirect it, right? Those are some examples of things that a CISC architecture would provide that a RISC architecture would not.
I have a question about VMM. So let's say I had Mac OS X VSMI. Would that be considered a VMM, without any modifications to it?
Is Mac OS X a VMM?
VSMI, yeah.
No.
Yeah.
Yosemite.
Yosemite.
Okay, no, it's not a VMM.
So what would I have to do to make it a VMM?
You'd have to go get like KVM or something, which KVM works on Linux. I don't know what VMMs. We will have virtual PC, probably.
So on Linux, I would get KVM.
On Linux, you get KVM.
And KVM is something I can install.
Yep, it says kernel module that you install in Linux,
Okay.
and that provides you the VMM.
Oh, yeah, okay.
Yeah. So
Yosemite.
Yosemite doesn't. No. Okay. Continuing on directly with this hardware virtualization. So we have the root mode. We have the non-root mode. So let's look at an example here, right, in a little more detail. So we've got the root mode, which is running our VMM, And it has the VM control state here. So that's going to contain information like what the page table is for it, let's say. And then in the non-root mode, we have our CPL0, so we're running our guest OS, and the CPL3, we're running our user program. And VM launch, VM resume, VM exit. So we exit out of the VM like on an EPT page fault, not on a guest OS page table fault, right? Because if the guest OS page table faults, we want that to go to the guest OS. So that would go to the non-root mode. But if the root mode extended page table faults, we want to go to the VMM. There's some trap and emulate stuff you can configure. So there's some configuration you can do for this basically. Interrupt will, for the most part, cause you to exit, although you can configure some to go directly stay in the root mode. And then you can enter, and it takes like about 200 cycles. So we can go up and down with sort of VM enter, VM exit type things between the root mode and the non-root mode. And within each of these, to go from CPL0 to CPL3 and back are our standard approaches. So from 3 to 0, we do some form of an interrupt, a trap. So we have these two layers. We talked about that. And that's part of what's needed, what we'd like for the hardware support for virtual machines. Another thing we'd like, let's say I want to hook up an I/O device to a guest OS, like an E1000. Okay? So I've got an E1000 on my hardware, and I want to hook that up. When you have an E1000 and you want to transmit a packet, how do you specify where that packet is? A transmit descriptor. And the transmit descriptor has in it an adder. So there's an address in it, and that address is of what type? Okay, UN64. And what kind of an address is it? It's a physical address. It's a really, really physical address, right? So because the I/O device doesn't use the MMU, because the MMU is on the CPU. So we have to use physical addresses. Well, that's going to break in our VM case because we would be using, in our guest OS, this guest physical address. And we would give this to our I/O device. And it would say, hey, I/O device, here's my packet, it's at this address. And the I/O device wouldn't be looking here, right? The I/O device would be looking at real physical address. So it would be missing this mapping. Does that problem make sense? All right. So the solution is throw some hardware at it. Okay? Throw an MMU in between the device and the bus. So it's similar to this MMU. What would we program it with? The same stuff that's in the EPT. Those same mappings. Does that make sense? Okay, so that solves one problem. We can directly control hardware and specify addresses to the I/O devices using from a guest OS. And the nice thing about that is then we don't have to get the VMM involved, right? So it can be quicker. So anytime you can directly execute, it goes faster. So we have these three sets of changes. The VTX, that is basically the root mode, not root mode. The page tables, having the two levels of page tables, and then also having the Iommu. So we've got what we're accustomed to: hardware, operating system, JOS or XV6, application sitting on top of that in the form of processes or environments. And they talk to the OS, and they never talk directly to the hardware. I mean, theoretically, yes, they are talking to the CPU. They're executing directly CPU instructions. But wouldn't it be nice and we've seen this before, if we could talk to the hardware. Okay? How do we want to talk to the hardware? Ideally, what if we just used hardware abstraction instead of providing some different abstraction? So if we want to change the page table mapping in JOS, we have calls to do that. Why not just go change the page table? Right. So here's what we're going to do. We're going to have here a VMM. That is, we're going to add code to our OS, just like we can add KVM installable module. We're going to add a module here. And this module is going to use this virtual machine hardware. So it's going to be in root mode. And then we're going to run this guy. In non-root mode. So we have isolation, right? This app is isolated from other apps, which is what we like with processes, for example. And this app is isolated from the OS. It's just isolated in a different way. It's isolated via root mode and not root mode than by CPL0 and CPL3. So this app, we can actually break apart, if we want, into two parts. We can have a CPL0 part, and we can have a CPL3 part. So we can choose to run in either mode. So this gives the application several things. One, it can directly modify page tables if it wants to do stuff with page table mappings. Two, it can use protection on parts of its code against itself. Why would you ever need to protect your code against yourself?
User input.
Okay, user input.
You could like Sandbox running other people's code.
Yeah, that's the key. Your code is not always your code, right? Your code, you use a JPEG decoder that you grabbed off the internet. No, I mean, it's a well-known GitHub project that does JPEG decoding. And so you take an arbitrary user JPEG, because you're a server or something, and you take that, and then you decode it, and unfortunately, there's a bug in their code. And through the decoding, it actually caused an exploit into your code. And like, you're unhappy, right? How could you stop that? With a normal process, you'd have to go create another process, and then somehow go communicate with it, maybe via shared memory or IPC or something. But in this case, we're talking about put your untrusted code here. So it's a beautiful sandbox. Okay. And then keep your trusted code in CPL0. Let's do a great example, a browser. Put your browser in CPL0 and put your plugin in CPL3. Okay? Or the JPEG decoding is a good example.
How can you trust the app's CPL0 though?
That's your code. So you're going to put the code you don't trust in CPL3. Depending on how much you trust your code, you might not have very much left in CPL0. Does that make sense? So, and actually, when I was at Google, the JPEG decoding is a good example. You were only allowed to run that in a sandbox. So you weren't allowed to just add that to your app. Assuming it was user-generated JPEGs. You mean like commercial?
Yeah, like
No.
Yosemite.
No. Okay.
This is weird design, right?
Yes, it is a weird design. It is. So we're going to use all this VMM hardware, but instead of having an entire OS in the non-root mode, we're going to just have a process in the non-root mode. Okay? So what if that process wants to, I don't know, allocate memory? Or let me do a simpler example. Let's say I want to make a TCP/IP call. I want to find my process ID. Let's go as simple as we can. I want to find my process ID. How do I normally do that? If I'm this guy, how do I find my process ID? System call, get PID. It's not caps. System call. And it returns us. Can I use a system call from my leftmost app? No. System calls are going to cause a fault within my non-root mode. So if I want to call from CPL3 to CPL0, I can have the equivalent of a system call, but I can't do that from here. So what can I do to get from here to here? VM call, and that's why it's here. I know I'm running on a VMM. I need to be running on a VMM because it provides me a lot of the things I need, like finding my PID, sending and receiving TCP/IP, doing all sorts of stuff. Okay, so a Dune process is still a Linux process. It still has memory. It can make system calls. The way it makes system calls is different, though. So it's through another mechanism. Fully isolated. But the way it gets isolated is different. Okay? And the EPT makes sure that it only gets the same physical pages it would normally get. Right? So the Linux OS would only provide this process with certain physical pages. The VMM is going to ensure that the EPT only goes to those same physical pages. Why do we want to do this? Well, we get the best of both worlds. We can get Linux environment and we get privileged instructions. We have this ability to use the different protection levels that the architecture provides, CPL0, CPL3. Why no one uses CPL1 and CPL2, I do not know. You could, right? You don't have to have just binary. Your exceptions are fast, right? When you get a page fault, it's doesn't have any extra software overhead. It's just the hardware finding that you had a page fault in your CR3 and then calling your page fault handler and you dealing with it. Okay? As opposed to, as we've seen, if you get a page fault in JOS, you've got to get a page fault in the operating system and then go figure out that it was a user one and then find out whether they had an upcall installed and then go call the upcall, right? Where the hardware would have sent it more directly. And then I say some interrupts are configured, we say here, to dispatch directly to non-root mode. How do we make a system call? If we do an interrupt, in the case of 80, 80 just happens to be what Linux uses for its system call interrupt. So what do we use in JOS? 30, yeah. So they use 80, it's fine. So what we do instead is we make a VM call. So we'll call VM call. We'll have to make sure to provide something that says this is a system call, and we'll have to provide the arguments. But there is a problem. We've got all this code out there, like let's say the standard library, calling printf, for instance. And printf eventually calls what system call? Write. Write is going to try to do an interrupt 80. And if we are in CPL0, when we do an interrupt 80, it's going to just call our own trap handler. And it's not what we want. So what could we do? We could go rewrite the libraries, but that's not fun. And we're here for fun. So we'll do this. We'll go ahead and let the interrupt 80 happen. So we're in our Dune process. Again, we're in CPL3, because in CPL0. In CPL3, what will happen on an interrupt 80? It'll go to CPL0 and will be in our system call handler, right? Okay. And actually, this is a key point right here. how do we ensure that our JPEG decoder doesn't... So we've got a JPEG decoder. What system calls should it be able to make? Maybe. I'm going to even say for JPEG, I'm going to give it the memory. I'm going to give it the address in memory where my JPEG is. So what system calls should it be able to make? None. I'm going to say you can't do anything. Just work in memory. Read from here, right to here. Right? Read the JPEG and write into this buffer. So if your JPEG library ever tried to make any system calls, you know it's bad. So if you're running your JPEG and you get a system call, you can look and decide, do I want this or not? Maybe I'll make a little list for every one of my untrusted code of what calls it's allowed to make. And that can easily be handled right here. But if I decide, yes, this is a valid system call, or I made it from CPL0, then I want to call the kernel that I'm running on. So, right, this is root mode, this is non-root mode, and I'm going to do that with a VM call. And then that little Dune module will just kind of send that over to the Linux system call handler.
Doesn't VM call go through the VMM?
Yes. So VM call actually goes into first the Dune module that's in here, and that will then feed it to the system call handler. And then we'll have to come back that same way. So basically, it's instead of the trap handler calling a system call handler, we'll have our Dune VM call handler call the system call handler. We see here just some overhead. So get PID has overhead. Why? Well, because we're having to make this jump and do a VM call and so on. Let's look at some examples of other things, though. So ptrace. Ptrace, does anyone know what ptrace is? So how do I, yes?
Oh, I know STS, sorry.
Okay, so ptrace is how GDB works. So if I want to debug another process, I can go to that other process and say, execute an instruction, and then return to me. And then execute another instruction and return to me, and so on. Okay? How can I cause one instruction to be executed? How could that possibly be implemented? Here's how you do it. Let's say you're right here, and you want to execute this instruction and stop at this instruction. You replace this instruction, you remember it, and then replace it with an interrupt. Interrupt, like let's say 3, which is called breakpoint. Exactly. And then when we come back to the breakpoint, what do? We go restore, whatever it was. Okay, so that's how single stepping works. Does that make sense? So anyway, there's a system call that allows you to control another process, assuming you have permission to do that, and single step, and that's the way that it works. It's expensive. In Dune, you can do something similar, because basically you get to put in the interrupt in there to execute, single step. Page faulting, much quicker to handle. Right? You don't have to be going through the page fault handler in Linux. This is the paper, remember, where we talked about the low-level primitives that could be provided, so applications could do cool things with the page tables. So they had like a trap, a protect, one page, and an unprotect. And if you do it in Linux, it's almost 10 times, right? An order of magnitude slower to be doing this, rather than just directly manipulating the page tables. So, Sandbox, we talked about this basically. So you're going to want to run a plugin, but limit what memory it can access. which is fine because you can just set up its own CPL, you can set up its own page table, and you can monitor or limit, filter the system calls. So if we're using Dune, we create a thread, which is the browser, running at CPL 0, and then create a thread for the plugin. And we can also create a thread for every page. Why not? Right? Make every page be isolated from every other page in the browser. And if one page dies, it doesn't kill the other pages. And so we set up mappings only for what's accessible. And then we run it at CPL 3. You try a system call, it's going to go into your CPL 0 handler, and it can then figure out what it wants to do. Questions? So yeah, this gives that example, or the diagram showing those plugins. And so they actually ran on the Dune browser some standard benchmarks. And you can see that most things were about the same. Some things were faster, and there were a few that were slower, sometimes by up to 20%. And most of that is due to the overhead of the extended page table. And there's a way to address that, which is, you remember, I think we talked about the fact that you can adjust your page size. So you can have a small page size, like our 4K page sizes, but you can also have larger page sizes, like 1 megabyte. And so if you go to larger page sizes, then you're using the cache more effectively, right? The TLB, because each entry in the TLB is covering more space. So they got better performance if they went ahead and used big pages for the extended page table rather than smaller pages. Similar to the exokernel idea, except in the exokernel, the idea is make system calls that allow you to do these things quickly. And in Dune, it's just provide raw access to the hardware via virtualization. Question for you. I've got, let's say, Yosemite, okay? And I install a VMM on that. What can I use again? VirtualBox. Okay, similar to KVM. So on top of VirtualBox, what do I run? I run on here Linux. Okay? Now, Linux is running on this virtual hardware. Why can't I run KVM here, and on top of this, run, let's say, Linux with Dune, with then my sandboxed browser or something? So this is recursive virtualization. And if you have something, and so if VirtualBox provides an accurate virtualization of x86, actually, what does it need to provide in order for me to run this? What does VirtualBox need to provide? Besides just regular x86 instructions. So we need regular x86 instructions. We need CPLs, right? We need to handle all that. What else do we need to handle in order to run this VMM on here? Exactly, the VM calls. So we need to support VM run, VM call, VM resume, and so on. If we do that, we can run another virtual machine monitor on top of this virtual machine monitor. And we can keep going. So Bertrand Russell was giving a talk, okay, to a general audience. And he was giving a talk about, I think it was the nature of the universe or something. Something about that. And cosmology of some sort. And then at the end of the talk, this old lady came up to him and said, Mr. Russell, you're just all wrong. In fact, the world sits on top of the back of a giant turtle. And he said, okay, what's the turtle sit on? And she said, oh, no, 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 no. You can't fool me that way. It's turtles all the way down. Okay, so it's kind of like this recursive one. And in fact, IBM has this recursive virtualization called turtles because of that. Okay. So as long as you can emulate it, as long as you can't tell the difference, then you can throw a VMM on it. So as long as your virtualization provides the so-called hardware virtualization instructions, it'll work. Monday, we're going to talk about using the same idea to do extremely fast network transmission.